Welcome. So we're going to discuss today axisymmetric elements and shell elements. I'll discuss axisymmetric first, and then shell elements. Then we'll have a special presentation by a colleague of ours here. So we discussed plane stress modeling, plane strain modeling. These are 2D elements. We discussed that. And plane stress typically is thin, like a thin plate, but all the loading is in plane to that plate. Plane strain will be, for example, a long tube, and every cross-section is the same as other cross-sections throughout the thickness, but you're looking at very long structures. Axisymmetric element is essentially you have a 2D cross-section, but it's revolved about an axis, okay? And it's also considered a 2D element. So in my book, I go into extensive detail on axisymmetric modeling. So some of the images are taken from there. And there are examples there you can go through and better understand these concepts. But in essence, in an axisymmetric model, what you really have, and I encounter this a lot, so this is used very frequently. You have a section or a part that you can represent just with a cross-section, because that cross-section, when you revolve it, is going to be representative of that 3D structure. And so it's very beneficial, and I've used it quite a bit. So in this example, you have a cross-section, and these are 2D elements, but in essence, you can rotate or revolve that to get a full 3D structure of that. Typically, the boundary conditions are symmetric about the axis of revolution. And all the boundary conditions are independent of the circumferential coordinates. So all the boundary conditions are typically either radial or along the cylinder, along the length of the cylinder. The material properties tend to be symmetric as well. Abacus does provide, and other codes like Nastran do provide, a generalized axisymmetric modeling approach, which allows you to apply torsion, which is, you can apply a load that's basically in the circumferential direction. They do have a specialized element for that. The strain displacement relationship in an axisymmetric element, and by the way, when I discuss this, a lot of the details are in my book. They discuss where this axisymmetric strain displacements come from. So I'm not going to devote my time in explaining where they come from. I'm just going to tell you that the strains for an axisymmetric formulation are given by this. And you will see here epsilon RR is derivative of u respect to r, epsilon theta theta, so the circumferential strain, so the strain in circumference direction, that strain, is equal to u over r. And epsilon z is derivative of w respect to z. And then the shear strain is basically the change in angle, is the derivative of w respect to r, and then u respect to z. And the important thing here is to understand that r is a coordinate in this direction, in the radial direction. W is the displacement, sorry, r is a coordinate in this direction, z is the coordinate in the along the axis of this part. R and Z represent together the axisymmetric coordinate system. U and W represent the deflections. So U represents the radial deflection, while W represents the deflection in the Z direction. Okay? So these two together basically are the displacement fields of interest. Those are the unknowns of the problem. Okay? Don't confuse these R with the R we use in as a parametric formulation for a triangle. Be very careful. This R is the radial coordinate in a 2D axisymmetric formulation, while Z is basically the coordinate for the axis of revolution. Okay. And so, as usual, what I can do, some tricks here, I can take the strain displacement relationships, which are given here, and I can put them in a form that I can use them later on for finite element formulation. So if you took the first row, I call this the differential operator L, if I take the first row, multiply by this column, I get that equation, that relationship. If I take this row times that column, I get that relationship, and so forth. You can see that it works out very nicely. Okay, and so this is nice because I can keep everything in compact form. I can use it later on for my finite element formulation. Is that clear? So you'll be doing some of this for the subsequent, basically final. I call it homework. Is an exam. The constitutive law in a axisymmetric formulation, because I have 4 strains now that I need to take care of, then you're going to have a 4x4 stress-strain relationship. So the stresses in the left-hand side, which are sigma RR, sigma theta theta, sigma ZZ, and sigma RZ, are related to the strains through this constitutive behavior. This is Hooke's law for that. You can see here that it has similarities to the plane strain formulation. Makes sense because in a plane strain, don't you think you have an infinite, basically infinite, is very long in one direction? So it makes sense because axisymmetric in some sense is infinite in the circumferential direction. So that's why the constitutive laws are similar in many ways. Okay, but in essence, please look at that. It's described in the book more, but I'm just giving you the general formulas for this. The equilibrium equations can also be derived very quickly. We're not going to use them because I'm going to use the total potential energy today to derive all the equations for both shells and plates and axisymmetric modeling. It just makes it easier, quicker. But I do want to spend some time to describe for you the stress states we're talking about. So when I look at a little cube here, little square from my axisymmetric modeling, and remember, look at this cross-section. Sometimes it takes time to visualize it, but this cross-section, when you revolve it, you get a 3D body. Can you visualize that? Okay. And so if I take a little square there, I can look at it. And what I see there is that the stress, sigma ZZ and sigma ZZ, acts to stretch that little square in the Z direction along the axis of revolution. Sigma RR, what it does, its job is basically, it produces internal stresses due to the radial deformation. So it acts to stretch or compress that in this direction, along the radial direction. You also have a shear stress, sigma RZ and sigma RZ. That's the change in angle in that plane, in this plane. So if I have an initially square 90-degree corner, that corner could change angles, and that represents a shear strain in that plane, shear stress in that plane. And so now I'm missing sigma theta theta. Sigma theta theta is a circumferential stress, okay? The hoop stress, we call that the hoop stress. While sigma ZZ here is called the axial stress. So for example, let me check your knowledge on mechanics of materials. If I have a cylindrical pressure vessel, and it's pressurized with a pressure P, and the radius is R, the thickness of the wall is T. What is the hoop stress? PR over T. Who said that? Good job. That's the hoop stress. What is the axial stress? PR over 2T. Okay? The pressure times the radius divided by twice the thickness. That's the axial. So that, for example, in that example, sigma ZZ will be equal to PR over 2T. And then you will have a hoop stress, which I'm not showing you here because it's out of plane. That hoop stress, sigma theta theta, will be equal to PR over T. Is that clear? So we're going to make that a problem like that. So you can do it by hand, and you will get PR over 2T. You'll get PR over T, and then you can compare against your hand calculations and abacus. So we'll do it that way. It's a good, simple problem for axisymmetric modeling. Okay? So given the strain displacement relationships, given the constitutive law that relates stress to strain through Hooke's law, given the equilibrium equations, now I have basically 10 unknowns, okay, 10 equations, because I have, in the constitutive law, I have 4 equations. Here I have 2 equations. And then I have the strain displacement relationship, that's another 4 equations. I have 10 equations, I have 10 unknowns, and what we can do is write everything in terms of displacements and then solve it using weak form. That's what we could do. But what we're going to do instead is use the total potential energy as an approach to solve this problem. So if I look at total potential energy, the full equation looks like this. I've changed everything. Before, if you remember, we were using sigma xx, epsilon xx, sigma yy, y, and so forth. But I'm going to change the variable so that we're consistent to this convention that we're talking about. Here, u is the radial deflection, v is the deflection in the hoop direction, and then w is going to be the axial deflection of that part. In this scenario, we're going to assume that the dependence on theta is not present, so that v is not present in our equation, and then any derivatives with respect to theta are also gone. So we only have radial dependence and axial dependence. And so when I look at that, this equation, which is the total potential energy, the first term corresponds to the strain energy of the system. The second part of the equation corresponds to the potential energy due to the applied loads. What I can do, I can simplify this equation into this one by removing all the terms that don't exist. So for example, we already showed you that the strain displacement relationship, that there's 4 out of 6 that are important, right? The other 2 are not present. And so what you see here is a simplification. You can see that some terms have gone away. The r theta term is not present, and the z theta term is not present. The rest of the terms are present because they're non-zero, and they're important. For example, these represent the strain energy density due to the radial deformation. These represent the strain energy density due to the deformation in the z direction, the axial direction, and so forth. Okay. And then you also have something that I have done. And you will see here that dv has been transformed to 2 pi r dr dz, because that's your differential volume in a solid or revolution. So the main difference you're going to see here compared to plane strain and plane stress, that maybe the only difference actually, or primary difference, is really the differential volume. The differential volume is going to look like 2 pi r dr dz. That's the main difference here. 2 pi, of course, is constant. You can bring it ahead. You also have the body forces. We are not going to apply any hoop body forces, so therefore b theta goes away, and we're not looking at any deformations in the hoop direction. So that's why v is 0, and so we're going to remove that. For traction forces, we plan to apply traction forces in the plane of r and z, the radial and the axial axis. So basically, traction forces could be applied, for example, along this surface. Along this surface, that surface is basically in that plane. So if I could apply pressure, for example, right? So that's an excellent example of a traction force you could apply. Another force you could apply is a traction force on this surface along the z-axis, right? So, but we're going to apply only traction forces in this surface, not in the hoop direction. Okay, another thing I want you to notice is that body forces, also the volume, the differential volume has been transformed to 2 pi r dr dc. Again, don't confuse this r with the r and s in the triangular isoparametric formulation. It's not the same, okay? This r is a radial coordinate in axisymmetric modeling. By convention, r is equal to 0 at the axis of revolution, and then r is some value away from the axis of revolution. Okay, that's very important to keep in mind. All right, and then so let's look at total potential energy. This is the total potential energy in compact form. So there's a column of stresses, there's a row of strains, or sorry, there's the row of stresses because it's sigma transpose. Strain is a column of, strain is a column, and then you have B bold, U bold, and so forth. And again, you see here this 2 pi r dr dz. So we've already integrated in the hoop direction. We've eliminated the hoop direction out of the integral. So now the integrals are these are area integrals now. Okay. So strain is given by this equation here. I already showed you that's L bold U. I can come up with L bold for my problem. This is a constitutive law, and the stresses and the unknown fields, displacement fields, are U and W, the radial deflection and the axial deflection. Do you guys have any questions? I'm going a little bit fast, potentially. You follow? You track?
The top one is just one equation.
How many equations you see there?
4.
You see 4 equations in the total potential energy? How many vote that there's 4 equations there? So the total potential energy is a single scalar quantity. So pi is a scalar quantity, so there's only one equation here. And we know that because, for example, sigma bold transpose is a 1 by 4, and this is a 4 by 1, so I get a 1 by 1, and so forth. You guys can check the rest. Okay. Any questions on this? So in plane strain and plane stress, we did have 2 unknown quantities, the displacements in the U direction, the displacements in the V direction, so vertical and horizontal. But in that case, we only had, a 3 by 3 stiffness matrix. Here we have 4 by 4 because the hoop direction contributes in the stiffness matrix. That's what makes this different compared to plane stress and plane strain. Okay, makes sense, don't you think? If the hoop direction had no stiffness, can you pressurize a cylindrical pressure vessel very easily? Yeah, it will become like a balloon, right? Infinite. It will deform infinitely. You need a hoop, like a band in that direction, stiffness in that direction, to prevent the hoop, the radial expansion of that vessel, right? So that's why the hoop stress is important, and you will develop one. Okay, you will come up with one, a hoop stress, which is we know for cylindrical pressure vessel is PR over T. Okay, all right. So I am ready now to look at the approximation function. We're going to be using Riley-Ritz. The approximation function is going to have, in this case, I have 2 unknowns. These are the unknowns I'm interested in, U and W. Once I know those unknowns, I know the strains. Once I know the strains, I know the stresses, right? And so, again, I'm going to make U, I'm going to interpolate U, so it's a function of the unknown coefficients, which are the nodal unknowns, U1, U2, U3, and so forth up to UM. Because I could have a triangular element, a square element, I could have a second-order triangular element, second-order quadrilateral element, Q8, Q9. Well, why would I make it generic? That way you can choose the one you want, right? So we could do that. So you can see that U becomes equal to N1 times U1, N2 times U2, plus N3 times U3, and so forth. And then for W, we're going to use the same interpolation functions, and I get N1 times W1, N2 plus, times W2, plus N3 times W3, and so forth. I can put everything in compact form, N bold, Q bold. I'll make L bold into this, right? So then what I'll do, I'll substitute these relationships. For example, we know that stress is constitutive law times strain. You agree? That's what that used to be. It was a stress here, right? You agree? So C times epsilon, and we already said that strain is L times U. This L bold times the displacement field. Okay, so that's that. And this used to be strain bold. I'm going to make a LU bold so that is strain. So then I have stress times strain. Okay, and the rest stays the same. I'm going to leave everything else the same. And what I'll do next is discretize the equations by substituting the approximation function, because that's how Riley-Ritz work. So for U, I'll make it N bold times Q. And again, the unknown coefficients become Q. The shape functions are the N bold. And so I'll put that in there, N bold Q, N bold Q. You can see here that U, let's see, oh yeah, U bold transpose, Q transpose, N bold transpose. I'll put all that in there. And then now I can write everything in this format, right? Okay. So I've basically applied transpose to Q bold, so it becomes a head. Then I apply transpose to L times N, and then I apply transpose to C. But C is symmetric. You agree? So that's why there's no transpose on that one. Okay. So that is the total potential energy in terms. Now the total potential energy. Will you agree that the total potential energy is a function now? It's only a function now of unknown coefficients, unknown nodal values, right? Because the only unknowns now are Q, and Q are these nodal values, U1 and so forth. Everything else here is known, and that is the only function. Is only a function of those variables now. And so now I can take Riley-Ritz and apply it. And this is pi, by the way. I made ln Q. I basically made that B bold. Okay. So just to simplify a little bit more for our purposes. And then I can now minimize this equation, which is pi, relative to the Q's. Each of the Q's, Q1, Q2, Q3. How many equations will I get? I'll get 2m. 2m equations because I have m on nodes, m nodes. I have 2 degrees of freedom per node. So I should get 2m equations when I do that. But, you already practiced that in the homework 2 or 3. So why I'm going to make you take the derivatives with respect to each of them, Q1, Q2. Well, I taught you a trick. Basically, get rid of this Q bold, transpose 1/2. Get rid of that, and that's the equation you'll get at the end. Okay? And so that is the element formulation for a axisymmetric model. Okay? And now this integral is over an area, and that area represents the cross-sectional area of the triangle. Okay? You're not looking at theta anymore. We already integrated in the theta direction, and that's represented by this 2 pi r here. Okay? It's already given there. All right, so that is the element formulation. Any questions on this so far? We're good? Therefore, the element formulation is as follows. So you have this equation here. And now what I'm going to do, I'm going to go to isoparametric formulation because it's convenient. And so my book actually, instead of using for a triangular element, for example, instead of using the R and S coordinate system, we don't want to do that. Because R means radial coordinates here. You don't want to mix the R in isoparametric with the R here, which is radial. So by convention for axisymmetric modeling, we use C and eta for isoparametric formulations. And so the thing I want to show you here is the coordinates of the triangle now, or this rectangle or quadrilateral, are R1 and Z1. The R1 is a radial coordinate, the location of that node in the radial direction. Z1 represents the coordinate along the axis of that part. You follow me? Yeah. So for example, let me go back. So for example, this point here, right? R represents the radial location from the axis of revolution, and Z represents the height from Z equals 0, right? So that's the location R comma Z, okay? R comma Z. And so what we're doing here, you're going to put the pairs of the coordinates of those nodes here, and that's what you put there. Of course, as a column, but to save space, I put it as a row, but I put transpose there, so you don't forget it's a column, okay? And I want to point out that we're going to interpolate we're going to map it. So if I have a triangular a triangle that is a shape of random shape, I can make it into a standard shape. Or if you have a quadrilateral that has none of the angles are 90 degrees, I can make it a square, right? That goes from -1 to 1. And so because of that, we're going to interpolate R and Z into the psi eta coordinate system. And this coordinate system is the one for the standard element, the triangle with a right side triangle, or for a quadrilateral, it's a square. And so then the shape functions, again, is just n1, n2. But now these n's are now a function of C and eta. That's the part to remember there. And again, I'll just put it into n bold C, and this contains now the geometry information, this right here. And if I know, I want you to see if you agree with me. If I know R and Z, can I calculate the Jacobian? Because n's for either triangle or square or second order square or second order triangle, for any of those cases, right? The n's are known in that coordinate system, in this map, in this standard element, okay? You may not realize that I kind of skipped some steps. I'm doing that because I think you're an expert now. And for n equals 3, for a triangle, that's your standard element, right? Those are the shape functions. 1 minus psi minus eta, n2 is psi, n3 is eta. Before, we were using R and S here. We don't want to do that. Let me remind you, because people will make a mistake. We're not doing that because then the R here in this system will get confused with the radial coordinate. That's why we're not doing that. We're changing everything to psi and eta. For m equals 4, the shape functions are also given here. We've all derived them, but you guys all follow it now. And you know that these shape functions satisfy partition unity. You can add them up, you'll get 1. They satisfy Kronecker delta property, and so forth. Okay, with this information, we're primed to now turn our isoparametric formulation into an integral. It goes -1 to 1. In both cases, -1 to 1, -1 to 1, for a quadrilateral, right, which became a square. And then have the determinant of J bold. And the thing I want to point out now is you have an R here. Can't forget that for axisymmetric modeling. And the R is going to add more complexity to this integral, but it doesn't matter because you're going to use Gaussian quadrature, which will take care of that. And so that's what you get, okay? And you also realize for the B bolds, you're going to have to calculate these derivatives here. Sorry, these derivatives here. And so you have to calculate these derivatives here. What we're going to do instead is invert this chain rule differentiation. And when I do that, that's my Jacobian inverse. And now I'm primed to substitute that into my B bold matrix. My B bold matrix, okay? Remember that if I have these calculations, these numbers, don't you agree that, for example, for shape function 1, which is this block here, you agree that derivative n1 respect to r can be calculated now because I have it from here? Yeah, I have the Jacobian. I have the Jacobian. I have these two calculated. I can get them, right? If I know n as a function of c and I have n as a function of eta, I know these numbers. I know the Jacobian. Then I can do this calculation to get these components, which can be filled out here for each of these blocks here, okay? And then again, BI is given here. I just put it there for completeness, but I didn't have to do that. I want you to notice one thing, is that you do have a 1 over r, and so that's going to come here as a derivative of ani with respect to r, okay? So important to remember that. You guys have any questions on this? No questions? let's continue. So if I have a BIs, I can get all these blocks, okay? And then I'm ready to, and then for a triangular element, which is going to be the case, you can have 0 to 1 minus eta, 0 to 1, and then you have that integration, okay? So that's the only difference between quadrilateral and triangle. The limits of integration change. The rules of integration change also. Those rules change also. Okay. With that said, I think I do want to describe what Abacus will be using. In Abacus, they use a CAX4 for quadrilateral element, CAX8 for second order quadrilateral element, CAX3 for triangular element, and CAX6 for second order triangular element. They also have the ability to do generalized axisymmetric modeling. And for generalized axisymmetric modeling, you'll add a G here in front. The CGAX4 allows you to apply torsion. It's incredible what it can do with that. You can do things with that element that you'll be really, really surprised. You can do composites. You can apply torsion. It's really impressive. The Abacus, and then if you read the theory manual, I think you will follow it. Because if you're learning in this class, you should be able to follow the manual. In Abacus, axisymmetric formulation uses the following coordinate system. This is a trick thing here that I want to make sure you follow it. Instead of reading this, I want to take you back to the picture so you don't get confused. So in Abacus, take your solid of revolution, your axial, your axis of revolution is going to be y, not z. Okay? Keep that in mind. So instead of z, which is our formulation, in Abacus, the axis of revolution is y. Okay? The radial coordinate r is x. Write that down. Are you following?
Yes.
I'm telling you this because I've seen people create axisymmetric models and they don't make sense. Okay? Abacus also allows you to visualize a 3D field, so you can actually mesh that, and then you can revolve it 360 to see if that is correct. Okay? Anyway, do you guys get that? So R is x. So my opinion is that you want to put a node at x equals 0 and y equals 0, and then at y equals 1. That way you know where the axis is, and everything has to be from there. Okay? That's what's going to be revolving. Well, Abacus will do the revolution for you. You don't have to do anything else. I do want to cover, I explained it here in words, but I think visually was better. One point I want to make is how to handle the tractions. That can be a little bit tricky here. So these tractions need to be considered carefully. You can see here the traction in this case, if I'm applying pressure to a single element. Don't you agree that this pressure is going to cause a hoop stress? Yeah, because if you revolve this, that ring, I'm applying pressure to that ring in the inside, it wants to expand that ring, right? But the ring has stiffness, so it's going to resist that. And so it's going to produce a stress, which is PR over T. And hopefully, if I were to do this in Abacus, it should be P times R, mean radius, divided by thickness of that. It should come up about the same, okay, if I ran this in Abacus. Okay, so the pressure is applied in the local connectivity. I made it up, 1, 2. I could have done 2, 3, 3, 4, it doesn't matter. So the pressure is applied on this surface, which is joined by local nodal numbering 1, 2. Okay? And so in a quadrilateral element, this is getting mapped to this edge here. Okay? So therefore, and then the tractions are clearly, you know what they are. The tractions are P in the radial direction. Do you guys see any tractions in the Z direction? 0, so that makes sense. P 0 there. And then you're ready. So one thing, you have your N transpose bold. That's important, right? And the ds has to be taken care of very carefully. This ds is basically 2 pi r, right? Because I'm looking at the surface, this surface here. That's the pressure supplied to that surface. You agree? So I have 2 pi r times this distance, basically. right? That's the area where that pressure is applied. So that's why you see a 2 pi r p out here, okay? This rp is the distance between this center axis of revolution to where this pressure is applied, okay? And then I have deep C. And then I have the same things we discussed before. We had to turn this differential element into a square root, okay? And you can then go from there, okay? And it will be simple from there. All right. Any questions? Because you know R as a function of C and Z as a function of C, so you can take these derivatives and evaluate all these at eta equals minus 1. We know we have to evaluate these at eta equals minus 1 because this surface maps to this surface, and that surface is at eta equals minus 1. And we know the differential element is deep C. That's why you see a square root here that looks like this with a deep C there. Okay? If my local coordinate system for this quadrilateral element was 2, 3, say, 2, 3. Then you have to look at 2, 3 here, right? And then now this is evaluated at C equals 1 because I'm the edge. And my differential element now is d eta because I have to integrate along that edge. Okay? Sorry? Well, you have to follow whatever this is. So if this is 2, whatever this is, if this is 2, 3, doesn't matter. That edge gets mapped here. Because your elements can only be correct if they're in the counterclockwise. So the node numbering has to be counterclockwise for plane stress, plane strain, and axisymmetric modeling. So it's always going to match the node numbering. Okay, let's move to the next one. Plate elements. Okay? Now, I'm not going to expect anyone here to become an expert on this stuff. Because I teach a whole course in composites, and it takes 15 weeks, and it goes into very deep detail. But what I'm going to do instead is I'm going to give you the highlights, okay, of plate elements. And I'll give you an example, and then after that, I'll give you an application. And what I really want you to do is just pay attention the best you can, and I'm just going to give the points that are important, okay? Although I'll go into some detail. I will go to the same level of detail, but I'm not expecting anyone here to become an expert overnight, okay? This takes time to understand. All right, so for plate elements, and I'll try to explain it as simple as I can, okay? And we'll get there, okay? But you have to trust me as I go through this. So what are plates? What can be represented as a plate? So what can be represented as a plate is you have a three-dimensional body, but one of the dimensions is thin compared to the other dimensions. So, for example, the table that you have in front of you can be considered a plate because one of the dimensions is much smaller than the length and the width. You agree? For example, in other examples that we'll see later, you'll see that the dimensions will be thin in one direction but not others. For example, take a cylindrical pressure vessel, right? So in that case, the wall could be thin, agreed? But the other lengths are long. So the circumferential direction is long and the axial direction is long. And so that case can be modeled as a plate because, or a shell in that case, because only one dimension is thin. So using three-dimensional elements to model the thickness does not make any sense. You can just follow the deformation of the structure, just following the mid-surface, okay? And so typically what you will see is that in this theory, you follow the mid-surface in the deformation process. So this is not very different from or the Bernoulli beam or Timoshenko beam, where you have a neutral axis, right? And so the deformation of the beam is represented by a neutral axis. In plates, the difference is that you have a mid-surface. And the deformation of that mid-surface tells you how the rest of the thickness is deforming and how everything else is deformed. Does that make sense? Any questions on that? Okay, I'm going to be covering one of the theories that Abacus has implemented in their code, which is called middling plates. Now, they have the ability to model thin plates as well, The one I'm going to cover is for thick plates, but it will also be able to cover very well thin plates. But there's other things that need to be done, and I won't have time to cover in this course, okay? But if you learn this, then you'll learn the basic approach for plates. So these are 3D structural representation of a plate. I don't want to have to put 10 elements through a thickness there. 3D solids, 10, and then I have a bunch of elements everywhere. It's just too computationally expensive. Why not just follow the mid-surface and then just follow that, right? That's a mid-surface right there. And so if I track that, then I know the deformation of the system, the structural system, and I can go from there. And so how many elements I have through a thickness here? 1. Just that shell element, the element that's meshing this. So it's not 2D because this one this particular element can actually deform in all 3 directions. Through a thickness, in plane, all directions, rotations, and so forth. So it's different from 2D from that perspective. In 2D, we only have deflections in the plane of the page, okay, and axisymmetric. And so I want you to also notice that the displacements in the mid-surface only depend on x and y. Only x and y. Here's an example that Leonardo helped me construct. But you can see here, these are 3D brick elements. And you can see here for 3D brick elements, with 3 elements through a thickness, I get the same out-of-plane deflection. And we exaggerated the deflection. It's like 2,300 inches. I don't think that's going to happen. But you can see here that if I model this with the shell elements, I get the same answer in essence. I mean, it's basically very similar. In fact, if I use just one row of elements, this one is actually not going to perform as good. Okay? Because this one is going to have some issues that we talked about last week. Or sorry, the last lecture, which is basically you get some locking, right? We talked about that for quadrilaterals. In a single row, you get some issues. Remember that? Okay. And so what are the displacement assumptions in this theory? Basically what we're saying is that the deflections in all 3 directions depend on x, y, and z, fine, but they explicitly, right, depend on u, c, v, c, and w. U, v, and w here represent the deflections of this plate in all 3 directions, x, y, and z. And I give you here the deflections. Okay. The point I want to make here is that this u naught, when you see this u naught, v naught, and w, these ones here represent the deflections of the mid-surface alone. Okay. And then these rotations, which is cx, which is a rotation about x, and then cy, which is a rotation about the y-axis. These rotations together are the ones that are able to provide a deflection through a thickness of that plate. Okay. And so in this theory, how many unknowns you see here? How many unknowns do you think we have? 5. We have 1, 2, 3, 4, 5. 5 unknowns. So now I have to have, I want to have more degrees of freedom per node. Okay. Any questions on this? So we have the unknowns, which are the deflections of this mid-surface, okay? And then we have these rotations, okay? They're similar to, these are similar, these CX and CY are similar to what we derived for Timoshenko beam, right? Very similar to that, okay? So, and then U, V, and W represent the deflections in all 3 directions, okay? And W is the deflection out of plane. And while U and V represent the in plane. So for example, if somebody took, I don't know why anybody will do that, but take this table, put it against that wall, and push against that wall, that's the in plane direction. If you put weight into this, that's the out of plane direction. Okay, but it's perpendicular to the plane of that mid surface. Okay, so this is called out of plane. This and this is called in plane. These two right here. These are the in plane directions of the plate. All right. So Sorry? This one right here represents the mid-surface deformations. And so you can see here at the top of the plate, so take the top of the plate. Top of the plate, say the thickness is h. The mid-surface is right in the middle. Then what is z at the top of the plate? H half, right? H half. So then the deflection on the top surface is u equals u naught plus h half times cx, right? But at the mid-surface, when z is 0, which is the mid-surface, then this goes away, and this becomes now the deflections of the mid-surface. You follow me?
So at mid-surface, we have no deflection in z direction.
Sorry?
At mid-surface, we have no deflection in z direction.
You have deflections in the mid-surface, so when z is 0, right, you still have deflections in the mid-surface. One thing we're assuming here is that the deflections at the outer plane deflections of this plate, doesn't matter where you're in the thickness, W is going to deform the same way. That's the only thing we're doing with this outer plane. These ones will change depending upon what Z is. Okay. So now I'm going to take and calculate the strains. You guys know the formula for strain, remember? And honestly, all of this is actually quite systematic. So if you just trust the system, don't worry about the math, but just understand the basics. I think you'll follow this very well. For example, what is the strain epsilon xx? Anybody knows? What is epsilon xx, the strain in the axial direction? Derivative of u respect to x, right? So then I have derivative of u respect to x of all of this. Right? So that's the first equation you see there. Derivative of u not respect to x plus z derivative of c respect to x. Okay? Nothing special here so far. Derivative of epsilon y now can be calculated as well as derivative of v respect to y. That one gives you derivative of v naught respect to y plus z derivative of c y. Okay, that's that one right there. See that? Let's look at the strains in the shear strain, in-plane, the in-plane shear strain of that plate. The in-plane shear strain is basically the derivative of u respect to y plus the derivative of v respect to x. That is the formula. And comes from here. This is a general formula for that. So then this is what you get when you actually calculate it yourself. Okay. And then now you have the outer plane strains. The transverse, we call these the transverse strains to the plate. The strains are in the thickness direction. So these strains are easy. This is gamma, say gamma xz. Gamma xz, for example. What is the derivative of u respect to z? This one. Cx. What is the derivative of w respect to x? Just w, derivative of w respect to x. That's right there. This one right there. Okay. And the other shear strain is this one. Now you may ask me, wait, what happened here? Epsilon zz is not showing up. I have 5 of them. I have no epsilon zz. The reason is because we assume that w does not depend on z. So the deflection out of plane to that plate, okay, can I use this? So the deflection, okay, in this direction, so out of plane, that deflection w does not depend on the thickness. And it makes sense, doesn't it? I mean, if it's thin, you assume that every point there is going to move about the same. You agree? Yeah, it makes sense to me. And so that's why epsilon zz is 0 here. So now you have 5 non-zero strains, okay? And another thing I want to point out, you have the z that's out there, okay? All right, I don't pretend you're going to memorize this because I don't even have it memorized myself. So just remember at least the basics of what we're talking about here. So I can put it more conveniently, in a more nicer fashion. I can put it in compact form. My goal here is to do everything compact form because that's how Feynman works. If I can put everything in compact form, things will go faster. And so I've taken those strains in the previous page and put them in a different format. And I want you to notice here that if I make Z0, which is a mid-surface, this goes away, right? So this becomes a mid-surface strains. All these are the mid-surface strains to that plate, okay? I also can write it a little bit differently. And what people do, they put, so you can see these are the three-dimensional strains, you agree? Three-dimensional. But what you can do, you agree that when I put Z equals 0, this becomes a mid-surface strains? This we were talking about the mid-surface of the plate, right? So what people do, and it's not to confuse anyone, it's actually to help you, is they'll name these strains with a superscript not. So this superscript not. They do that so you know that the strains here are the mid-surface strains. That's the purpose of that. Okay, it's not to make the notation more confusing, it's to help you. Finally, these strains here represents, just like a Timoshenko beam and ordered Bernoulli beam, the curvatures. Remember the curvatures? So these strains represent the curvatures of that plate. Okay, so these are the curvatures of that plate. For example, in a plate, you can bend it, right? And then you'll get a curvature. That curvature represents the ones you see there. You will have a curve, but now you have two curvatures. Don't you agree? Can I use this folder again? This is going to, I have one curvature this way, right? Then I have another curvature this way, and the other one will be hard for me to do. But there's a double curvature, one going this way and then one going that way. Sorry. All right. You guys get it? All right. So these are the strain displacement relationships for a plate. I'm just reformatting a little bit everything so that it's cleaner. Okay. Let's look at we can now plug this into the strain energy, and I'm going to go for the kill right now. So strain energy density is 1/2 sigma bold transpose epsilon bold. And what I'm going to do, since there are 5 non-zero strains, I will have 5 stresses that go along with them. So I have sigma xx times epsilon xx. You agree? Sigma yy times epsilon yy, sigma xy times gamma xy, plus sigma yz times sigma yz, and then sigma xz times gamma xz. That's my strain energy. And so I will realize here very quickly that if I call this column here epsilon bold with superscript, that I get, basically I have the in-plane stresses, call those in-plane stresses sigma x, sigma y, and sigma xy. So that's a column of stresses there, okay? That column of stresses times this here. Okay, so I'll call this epsilon bold plus z plus this kappa bold. Okay, that's what I have there. So just looking at the in-plane stresses separately. Okay, it's convenient to do it that way. You guys follow this? At least up to here? So all I've done right now is create a column of sigma bold I, which is just, and I call it I for in-plane, for sigma xx, sigma yy, and sigma xy, just for those. Okay? And so if I call this epsilon naught plus z times that, kappa, then sigma xx times epsilon xx plus sigma yy times epsilon yy plus sigma xy gamma xy is basically this equation right here, up to here. Okay? Now I'll add the energy here due to the shear stresses, the transverse shear stresses, which is sigma xy, sigma yz times that plus sigma xz times that. So I'll put this as sigma bold shear, gamma shear, and those are the ones given there. So this is the transverse shear strain energy, this is the in-plane strain energy. It's convenient to have it separate for now. We'll combine them later. Any questions?
Could we replace shear strain by epsilon multiplied by ratio?
No. No, because, sorry, could you repeat?
Like,
Maybe I misunderstood.
So for like Timoshenko beam, we used the Russell's ratio to not have to like deal with shear strain.
Oh, yeah. So I'm going to take this to the next level. So today's lecture, I'm going to cover composites. So we're going to actually include composites here. So I don't want to make any assumptions. We're going to use pure, everything. So you can go to Abacus, put your pi angles, you can use it. Okay. So I don't want to make any assumptions. Isotropic, none of that. We're going to make it orthotropic. Okay, so any questions on this? Okay, so if I plug into my strain energy, what I have now is minus h half. So I can take my volume. Don't you agree I have the volume of dV, the dV volume? Now, since now everything is an explicit function of z, right? Everything has z in it. If you go back, actually, I'll show you what I mean. One more time. You agree that none of this stuff depends on z? Right? Except for here, it's explicit function of z. Because of that, I can do a trick. I can integrate now all my strains. I can now basically integrate this from minus h half to h half. So what I'll do, integrate through the thickness, leave the in-plane direction alone. Okay? Because my d volume will be taken care of that way. And this here is basically dz. Okay, that integral here. dz, and then this will be dx dy. And so, but I also realized it can be written this way. Sigma I bold transpose times epsilon this. Basically what I had in the previous page, you agree? The only thing, all these are a function of this right here. It's not a function of z. So what I can do, I can trick my integrals so that I have epsilon naught times that integral plus kappa times that integral plus gamma times that integral. This is the same thing as that. What I've done, I've tricked it. Instead of having epsilon here, I just took it out because it's not a function of z. Okay? Any questions on that? So this is going to become important when Christian talks about it, because these quantities here have meaning now. These quantities have meaning. I'll explain that meaning in the next page. So what is the meaning? So if you go to Abacus or Nastran, when you use plate elements, it's going to give you something called stress resultants. Okay? Sometimes it will give you stress resultants, you can get that, or you can get the actual stresses. Okay? But what I want to point out is that the integral from minus h half to h half of the stress bold dz, this is going to be nxx, nyy, and nxy. Okay? These are called the stress resultants because you took the stresses and you integrated through the thickness from minus h half to h half. Okay? So the way we look at that, we also call this stress resultant. So we've taken this stress right here, sigma xx, say, this one here, the sigma xx acts that way. We've integrated through the thickness, and then Christian is going to talk about per unit length, that this n is per unit length. There's a reason for that, is because I integrated the stress over that thickness. And so now it's per unit length. And so this nxx is actually considered a running line load, we call it also. Sigma yy is nyy, and then sigma xy is nxy. So that integral will give you this stress resultants. For a moment, you also get, I have to calculate the integral too, remember. Sigma z dz. So this one here is moments, and those moments are given here. You can check that these are moments. mxx, myy, and mxy. And I give you the conventions here in this picture so you can see what they are. Okay. And then finally I have sigma shears, which are through the thickness shears. And those shears I'm also integrating through the thickness, and we're going to call them q bold, or qx and qy, which is a shear in that direction. Okay. So in Nastran, can you confirm? In Nastran, they'll give you the n's, the m's, and the q's, I think. All of them, right? Yeah. So you'll get all of them. You'll get 6 plus 2 more, you'll get 8. So, not making that up, it's true. Okay.
What is the other two more?
These ones, the shears, the transverse shears. Okay. Okay, with that information, what I can do, I know this is m bold now. That's n, that's m, and that's q. I'll plug that in, and now my strain energy simplifies to something just like that. Something a little bit simpler to handle. Okay. Now I'm going to skip some steps now because this is the part that takes time to explain, and we don't have that much time. So I'm going to go straight to the bottom line here. This is a constitutive law that relates stress to strain. This relates stress to strain. And this is true for orthotropic material. And these quantities, E1, nu1, 2, nu2, 1, all these quantities can be measured. You can measure them. For example, you can in a single test you can get two values. For example, I can take a strip of composite material, all 0 degrees fibers, pre-preg and accurate and whatnot, and then in the one direction I'll test it and I'll get E11. But if I put a strain gauge in there, I can now get also, I'll get the modulus E11, but if I put a strain gauge in the other direction, in the y direction, I'll get the Poisson ratio, nu12. And then what I can do now is construct my specimen so there is a 90-degree specimen, so the fibers are perpendicular to the line of loading, and now I can get E22. And then from that way, you can actually get all the properties, okay? The G12 test, to get G12, you'll do a plus minus 45 off-axis test. That can give you G12 as well. So you take the plies, you put them plus minus 45, you test that, and you can get G12 if you strain gauge that correctly. So now all these properties can be measured, and if you know all these properties, you can get these Qs, okay? These Qs, and the formulas are given here and how to calculate the Qs. So the first question I want to ask you is, do you agree that I can get these Qs? Yeah? So if I know E11, I know the Poisson ratios, I gave you the formulas for Q, didn't I? So those Qs fully populate my matrix Q there. And then also the shear modulus can be measured by using a test called Isopescu testing. That'll give you G23 and G13. So I can measure these values, okay, in a lab environment. So with that, I have the Qs completely represented. If I know the Qs, I can calculate these invariants. We call these invariants, but don't worry about it. You can calculate these Qs. You agree? Because I know the Qs. So if I know the Qs, do I know the U's? If I know the U's, ooh, I can do that too. Because you know the ply angle. So you know if it's 0 degrees, 45 degrees, 30 degrees. So theta here represents the ply angle that you have. So say you have a 0 degree ply angle, then theta is 0. And then if theta is 0, what you're going to get is the Q bars. So anyway, you can get these Q bars, which is in essence what we're going to need for the next calculation. Anyway, so if you know modulus E11, E22, nu12, G12, G23, and G23, I know the Qs. If I know the Qs, I know the U's. And if I know the U's and I know the ply angle, then I know these Q bars, which I'm going to need in the next step. Okay? You follow?
That's Q global, right?
This Q bar is in a global orientation system. So I've transformed, and you can derive this yourself with a transformation matrix, which I think I covered in one of the lectures. So you can rotate, right, each ply to the global orientation. And so what we're going to do in the next step, we're going to use a Q bar. Okay? We're going to use a Q bar. You see this Q bar here? Do you agree that I could have 20, 30, 50 plies? Right? So when I integrate from minus h half to h half, right, what I'm going to do, I could integrate from minus h half to this, where this plies ends, plus integrate from here to where this plies ends, and so forth, all the way when I go all the way to the top, right? But I know the Q bars and I know the thetas for every ply. So I know the Q bars for every ply now because they're not now in global orientation. You agree? Yeah? And so that's why now I have to calculate these A's, B's, and D's, and the way to calculate them is using these coordinates for the thickness of where that location is. So say for ply number 1, ZK minus Z sub 0. You see that? Yeah? So that ply is here. This one here at the bottom. Okay? So I can calculate Q bar I know Q bar from the previous page, and I know the ply angle for that particular ply, and I know the location, so I can calculate this thickness. Okay, that's for A. For B, I have to calculate this. For D, I have to calculate that. It has a Z cube instead. You have to add them all up to get A, B, and D. Okay, A, B, and D. Are you tracking? Big picture perspective. I'm not asking to memorize any of this. I'm asking to kind of follow the big picture. A, B, and D, yeah. So A, B, and D are fully known. I'll explain that in a minute. Do I know A, B, and D for sure? 100%? How do I know that? I know E11. I know E22. I know Nu12. I know G12. I know G23 and G13. If I have those, I can calculate the Q's, right? I give you the formula. If I have the Q's and I know the ply angle, I can transform the ply angle to be in a global orientation, and that will create my Q bars. So what I discussed there is this page right here. I calculate all my Q bars. These Q bars are needed for me to calculate these A's. And these are fully known. You will know these A's because you know where the ply angle is, right? You know the ply angle of every single stack here, right? I know that. I know the thickness of every ply. So I know the location, ZK, ZK minus 1. I know all of that stuff. So if I know all of that stuff, can I do that summation? Yeah, I can do all these summations, okay? So with that information, I get A, B, and D, which is fully populated, or they're all numbers now, and I get this A, B, D, and D, okay? So what this is doing now, I want to explain it. This is called the axial, this is called the extensional stiffness matrix. This is called the bending stiffness matrix. And this B is a coupling between extension and bending. So let me take a composite that's not symmetric. If I take a composite that's plus 30 degrees, plus 45 degrees, it's not symmetric about the mid-surface. So the plies are going that way, the next ply is going that way too. And I load it up this way. What that plate is going to do is going to have a tendency to bend also. Although I'm applying axial loading alone, it's going to bend too. Do you know why? Because of this presence of this B matrix. Physically, that's what's happening. Also, if I apply moment to this plate, it's going to stretch a little bit or contract. Okay, you follow me? So they have physical meaning, and in fact, this will simplify for isotropic materials very quickly, right? Any questions on this? Again, not asking you to be an expert, but just kind of follow the steps that I've discussed so far. So I want you to notice how I've related N and M. I've related those to the strains in the mid-surface. Okay, these are the strains in the mid-surface, and also these are, I can relate the transverse shears to the transverse shears strains. Okay. Any questions? So I'm going to take this equation here. Okay, before I go to that one, I'll call this A bold. Can I do that? I'll call this B bold. Can I do that? I'll call this B bold and D bold. So I call it A bold, B bold, and D bold. Okay? And that way now I can simplify everything even more. Make it more compact even. Okay? Oh, and then I also made this N bold, and these are already, I gave it to you earlier, okay? All right. Nothing to fear because I know all these matrices. I know them very well, and they have names, okay? So, since I can relate M bold to epsilon bold, M bold to kappa bold, Q bold to gamma bold from the previous page, you agree? I can relate it. I can write N bold, and Q bold in terms of epsilon, kappa bold, and gamma into an equation that looks like this. Okay? And I can do that because, do you agree with me that N transpose bold plus M bold, if I put it in a column vector, times epsilon bold, kappa bold, that if I make M bold and M bold, I can substitute what that is, and it's basically this multiplied by that, isn't it? But now I have a transpose, that's the difference. Okay? This is fully symmetric here. Okay? And then I have this one here. I already know that Q is A times gamma, but A times gamma, that gives you transpose, and so that gives you that. And again, A is symmetric. That's why I don't have a transpose there. And that's why I don't have a transpose here. Any questions on that step? I can also now make it even more compact. So I'll put everything in one place. This is equivalent to that, basically. Now look at total potential energy to transverse loads, Q times W. Just add that one there. Okay. And I did this for a special case, of course. That's a special case, but I didn't make it generic. Okay. Let's call this whole thing C bold. Let's call this whole thing epsilon bold. And if that's epsilon bold, this epsilon transpose bold. Again, it's all keeping track of things. And I think in 2 minutes I can summarize everything we've done. Let's do it really quick. Really quick. We came up with these displacement assumptions. 5 unknowns. We have mid-surface displacements. We have rotations Cx and Cy. I took those displacements, calculated strains. I have 5 of them. Then I put in a form that's easy to follow because then these are mid-surface strains. And these are the strains represents the curvature. So I have curvatures. I have in-plane strains. Then I calculate strain energy, density. Then I calculate strain energy in the system. And then I define new quantities are N bold, M bold, and Q bold, which are basically force per unit length. And I define those here. Then I substitute that here. Then I want to get a relationship of M bold, Q bold, that is in terms of epsilon bold, kappa bold, and gamma bold. Then I calculated the Qs that basically relate stress to strain. And if I know E11, E22, Nu12, G12, I can calculate these Qs. If I know these Qs, I can calculate Q bar because that now is a transformation for every ply. So the Q bar is in the global orientation system. That's for single ply. Then I calculate A, B, and D. Very easy to do because I know the location of every ply. I know Q bar for every ply. So this is just a summation, straight summation. I give the derivation where this came from, but if you want it, I can give you my notes on that. So I have A, B, and D. A is the extensional stiffness matrix. B is the extensional bending stiffness matrix. So I can have coupling now. So if I apply axial loading, the structure bends, right? It can bend also if it's composites. And then D is the bending stiffness matrix. Okay, so I'm kind of summarizing that for you. Then I put it in a compact form. I recalculate strain energy, but now in terms of the constitutive matrix, the strains. I put this in a more compact form even. Call this C bold, this E, this epsilon, E transpose. Now I can calculate, now I want to relate, because now I'm going to find elements, right? I have a bunch of strains, 1, 2, 3, 4, 5, 6, 7, 8. So it makes sense. I have 6 strains, 6 resultants, the 3 N's, the 3 M's, the 2 Q's. And I can put this equation here, my differential operator, and these are my 5 unknowns, my 5 displacements that I don't know. These are the ones I want to find. And if I find these, I can multiply against that, and I'll get my strains. And if I know my strains, I know the stresses, right? Any questions on this? Or call this L bold, call this U bold. I'm getting closer now. I could use Riley-Ritz. I can approximate the solution for U, V, W, CX, CY. This came straight out of my composites class, so hopefully you follow it. But these are the unknown coefficients in Riley-Ritz. These are the basis functions. I plug that into my total potential energy. I take the derivative of pi with respect to each of the unknown coefficients equal to 0 and get the coefficients, right? But instead of that, we'll use this approach, which is finite elements. And now I'll take the displacements, okay, and I'll interpolate it so my unknown coefficient becomes the nodal unknowns, okay. And then I will also use shape functions that are the same for all of them, Okay, and these are my basis functions now. They'll satisfy partition unity. I can do a quadrilateral now with this. I can do a triangle. I can do second order element and so forth. I'll put this in a format that looks like U bold equals N bold times Q. And you know that this is going to look very weird. It's going to have, like if you saw the previous examples, didn't I have like N1 in the first row, then N1 the second row, then N1 the third row? I'll have 5 like that. N1, 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 everything's 0. N2, 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 N2. So it's going to be like very long. So instead, I want to shortcut it, show it to you. You put this in this form. So it's compact. You follow it? So my N bold contains a matrix that's 5 by 5M. And then the first block is a diagonals of N1. The second block is a diagonal of N2s. And if I multiply this by that, you will get these equations. Okay, now I'm ready to substitute that into my total potential energy. You agree that E bold is LU bold? This C is more complicated than it looks. It's AB, BD, and then, remember that one? Pretty big. You have to calculate all that stuff. U, I know that already, is N times Q. So plug that in there. Okay. And then here you go. Take the Q bold transpose out. Okay. There to pi respect to Q bold gives me my finite equation for finite element formulation for a composite plate. You follow the steps, kind of? Yeah? If not, I invite you to kind of review. You can review. You have the video available to you. Okay? All right. So let's do an abacus example. In abacus, let me show you how to do that. I'm not going to make you do that by hand. Okay? That's not happening. I will not do that to myself either. Okay? So here's a plate. I took three elements. These are the nodal information for that plate. Now I could have done a three-dimensional, but I kept the plate, flat. Okay. The element type is S4, shell element with 4 nodes. So this is the connectivity for that. I had to define orientation because I decided to do a composite example. So I defined the orientation so that the global x direction. Basically, I defined the orientation so I have the global x direction along the y-axis. And so here I provide x and y. So I define what x and y axes are. And any rotation I provided will be about the 3 axes. And this is my reference 0 degrees. I'm not rotating anything yet. The shell section definition is orientation global x. So I'm going to use that orientation. And all the angles I provide here will be relative to that reference, 0 degrees, and the orientation I provided there. Then I want to say composite because I decided to do composite. And so then I have the ply thickness. Each ply, you can put the thickness, can be different from each other. The important thing is that the first number here represents the OML, the location, the IML. The first ply you put onto your mandrel. Okay, so that's the first ply that goes there. The second ply is the one that goes above. And then you put all your plies, and the one outside here is the OML, the outside. Okay. Here are the ply angles. Carbon epoxy, I just give it a name. That's a composite material that I'm going to use. Who's going to be referenced here in the material card. And I put type equals lamina. And you can see here, these are the same coefficients. I only had to define this, if you remember earlier from my derivations. E11, E22, Nu12, G12, G13, and G23. I put some properties there from a book that I have, Isaac Daniel, Mechanics of Composite Materials, very good book. I just took one of them and just put the properties here for that. Okay. Then I ran a static step. I put a C load, a load of 100 pounds on this corner, 100 pounds this corner, and because of the ply angles I chose, you can see it's not symmetric about the mid-surface. When I applied this loading, it kind of twisted a little bit. You can see it's not quite. I mean, I didn't exaggerate the deformation, but it's going to twist a little bit. I did that on purpose, so you guys can see that. So here's an example for composite shell. Okay. Typical modeling issues. I'll come back to this next week. Abacus applications. Let's talk about abacus applications. So you can use shell elements to model structures in one dimension. The thickness is smaller than the other dimensions. Star shell section allows you to implement those. The shell elements will have displacement and rotational degrees of freedom. You guys already know what are the rotational degrees of freedom for us in the shell element formulation, which is Cx, Cy. The top surface of a conventional shell element is the surface in the positive normal direction and is also known as S-pos. In the negative direction is called S-neg. If you want to create like a contact, surface contact, you can call that surface out. Because while you have a shell element, you agree that you have a top surface and bottom surface. So the way Abacus tracks that is using the normal to that shell element. That way you can actually select that surface of that shell element for contact purposes. Abacus uses different element types. S, 8 is basically the number of nodes. R is whether it's reduced integration. 5 is whether you want 5 degrees of freedom. Our formulation was a 5 degree of freedom element in Nastran. Do you guys use a K6 rod? K6 rod? The reason is because the formulation there has 5 degrees of freedom, and you have a drilling degree of freedom, so the drilling degree of freedom is the rotation about the z-axis. Remember we didn't have one, right? So what's going to happen when I invert the stiffness matrix? I could have a singularity. So you understand what I'm saying? I have 5 degrees of freedom. U, V, W, Cx, Cy. I didn't have a Cz, a rotation about z. So now, because I have 0 there, when I invert the stiffness matrix, I could have an issue. So that, for example, Nastran will add a K6 rod to take care of that. Sorry? Yeah, like 100, right? No, normally we'd recommend 100. I've seen people use 1 and they will not get adequate responses. Abacus, you don't have to do that. Abacus will take care of that internally. Anyway, you guys can read this at your own pace. You can do thick conventional plates. The one I discussed today was thick conventional plates using Mindlin theory, which is more like Timoshenko. Abacus also provides S8R and S8RT elements. This T is for temperature. R is for reduced integration. You can also use other element types given here. These are other element types that can cover thin plates. So if you have a thin plate, you will use something like Order-Bernoulli, where Order-Bernoulli is similar to Kirchhoff thin plates. I didn't cover that here. I did Mindlin plates. Okay. Okay. All right, you guys can read that. All right, so here I'm going to move to application now, and just a second.
But eventually you go to FEM, and you really need that hand calc background to be able to validate any model that you create. So I'm just going to go over, first off, the general application. I work a lot of aircraft, jet trainers, a lot of other stuff I can't talk about. So the overall design process, usually where I work in is this area. I'm on the analysis side, and we work really closely with design side. So the design side gives us all the models, the CAD models that we use to generate a FEM. And so it's it's an iterative process, because they'll give us a design after we give them input. So we tell them how we want the structural arrangement. They'll lay it out in CATIA, SolidWorks, whatever CAD software that they use, and then we take that, we create a model, we run some initial cases, and we do our first initial sizing, and then we feed that back to design saying we want this part to be this thick, we want you to add a part here, we want you to take weight out here, and it's an iterative process. That's why this can take months. You go through phases of design cycles to go through that. So overall, most of these, all this that you see here is basically what constitutes an aircraft. So each of the things you see here can be represented with a particular element type. So skins, just like Vinay was talking about, that would be your quad elements. That would be your plate elements. Stringers are more, you would either use rod elements, which are bar elements in Abacus, or if you really care about the bending, you'd model them as beams. So it really depends on what kind of load you expect that member or that part, what kind of load it will take. So that, I would use a rod for that. I just care about the axial load that's going through there. Frames, you probably use frames or plate elements, ribs or plates. Most of it's going to be plates, with the exception of the, plug it in. There we go. I can go through all these, but the main takeaway is most of it is plates, with an exception of some 1D elements. So here it is, just kind of broken down. As far as how we use finite elements is, an airplane can be divided into its major components. The fuselage can be structurally decoupled from the wing. So can the horizontal tails. They're decoupled from the fuselage, the vertical tails, so that we can analyze those parts independently. We can have our own wing standalone models. And there's some clever ways of decoupling a structure based on how you join it together, so that any load inside the fuselage stays in the fuselage and doesn't transfer to the wing or vice versa. So I've dealt mainly with the wing, but I know enough about the fuselage and these horizontal stabilizers and vertical fins. These are basically wings, just at a different orientation. So here's an example of a really fine mesh plate element model. So I guess they're looking to read off the KTs. If you've heard of KTs, stress concentrations around cutouts. It's particularly fatigue. What is these just worried about? There you go. So they save 10 pounds per airplane, which translates to dollars. So in industry, there's no way to really quantify how much something is going to cost. So we have parametrics based on previous programs that tell us 1 pound of aluminum generally costs this amount. And that's why when you give a weight statement, that translates exactly to how much projected dollars that will cost. So that's what that's what's our job, is to take as much weight out of the aircraft, because it generally will be less expensive unless you use exotic materials. So here's a good example of a wing test. This is usually done to validate the structure. You can use it to validate your FEM as well if you do some vibrations testing. Here you can see these wiffle trees, because the wing takes evenly distributed pressure, but you can't really apply that to a wing. So you use these wiffle trees to kind of spread out the loads with pads, and you kind of have to try to match the loads that you see in flight and recreate them here. And so here's a pretty good comparison between the FEM, which is the analysis, versus the actual tests, and they're just looking at deflection. Here's some typical failure modes. I'm not really going to go over these too much. This just tells you if you're on the vertical fin group, you're going to primarily be worried about bird strike in this area. And if you look at other parts, you can clearly see the forward fuse. Anything that's in front is going to be looked at for bird strike. And yeah, I'll keep going with that. I'll talk a little bit about global versus local. A lot of times people are inclined to just take a model of a CAD part and just TET mesh it. What they call it TET blasting. Generally, at least where I work, we don't like to do that, because you want to be able to take your model and be able to understand the part well enough to know what type of load is going through each part, and use a 2D or a 1D element to represent that. But it has its applications in really local model like this. So here they're looks like they're really interested in this area. So you can see this was coarse modeled and this was fine mesh modeled. So it's an upper link torque. So I mainly dealt with the global loads FEM kind of stuff, which is really coarse. It's a really coarse FEM, and we keep it like that because you want to be able to iterate and change the FEM on the fly. When you start working with local detailed models, you'll notice that the time to work with these models, it can take weeks. It's usually a standalone project. It's usually for one-off projects. Say something happened during test and something broke and you want to figure out why. It's a one-off instance versus a global model is used for general sizing, like at a preliminary phase of a design. And so a local or a stress model is used for detailed sizing, whereas load FEM is used for preliminary sizing. One of the big takeaways is you never, ever read the output, the stress output from a loads model. The loads model is called a loads model because you extract the internal loads. Just like he was going over Vinay, he was going over the running loads. That's what you typically extract for a 2D element, for example. So you never write a margin to stress that you see in a local, really coarse model. It's acceptable to do that in a stress model. Once you know that your mesh refinement has converged. So you typically refine the mesh until your stress is not changing as you keep refining it with a certain 5% or so, then you're confident that your solution has converged for the stress. All right. So since I deal with wing, I thought I'd take a conventional wing. A wing is usually just made up of spars, ribs, and skin. And here's a wing on this side. Here's a cutout. And you typically take that and you simplify it. You have your spars, you have your ribs, and then you have your skin. And each of those components is modeled using different element types. So for the spars in a wing design, it's important to understand what kind of loads that they carry. So the spars will usually carry a majority of your wing shear and bending moment. I throw in a parenthesis in there because they carry the bending moment if and only if you design your wing to be a stress substructure versus a stress skin design. That just means what part of your wing is going to take the bending loads of the wing. So usually, conventionally, you build up I-beams for the spars, and the spars themselves take the majority of the bending. But you can also have a wing design where your skin is thick enough where that skin is able to take the wing bending loads, and you can thin out your webs of your spars, and you can thin down the caps of your spars. So it has its advantages and disadvantages. For the ribs, they're usually meant to carry shear loads, and they're meant to also break up the skin panels, because like Vinay's going to go over next week, he's going to talk about buckling, and rib spacing is really important for that. For the skin, they carry your shear load from torsion and wing bending moment, like I discussed about. If it's a stress skin design, it'll take wing bending moments. And it takes it as a force couple between your upper and lower skin. So if you're bending up, your upper skin will be in compression and your lower skin will be in tension. That's how it's taking the load. And those translate directly to in-plane loads that he was talking about, your running loads on the upper and lower skin. One more thing to mention is out-of-plane loads or out-of-plane moments. So the only thing that will produce that really typically is either punch loads, that punch load out of plane, just like he was talking about, or field pressures, at least for the wing. Typically your wing will carry field and it will be pressurized at a certain level. So you have to account for that in your analysis. So here's just a diagram kind of showing the running loads. I think Vinay has a similar diagram that we just went over a while ago. And they're in forces of units of force per unit length. And so I was kind of going online figuring out what's the best way to show what I do without having to go too much into detail of actually building the model, because I think building the model anyone can learn how to do. Anyone can take a CAD geometry and throw a mesh on it. They can throw in properties to it. They can assign thicknesses. So I just thought of a simple example. I found this online, and I said, this is a good example. This is a really simplified wing box. It has some kind of thickness to the wing. Usually you don't analyze this portion or this portion, because on a wing, this is your leading edge. If you picture the wing going this way, this would be your leading edge, and that's typically separate from your wing box. And then you have your trailing edge, which is usually your control surfaces. And so for the purpose of what I do, we usually decouple that as well. So the wing box can stand alone, and I can analyze that alone, and then I can just apply the loads that come in from the control surfaces and the leading edge to wherever they mate with the wing box. So here I have I'm going to call this my forward spar, my mid spar, and my aft spar. This is a cross section looking this way. Lower skin, upper skin. I said make it 180 inches long out of plane. Throw in 7 ribs at 30 inches apart. I'll make everything 0.1 inches thin. And then for the caps, which are right here, so think about it as an I-beam or a C-channel, either or. The cap would be 2 inches this way and 0.2 inches thick. And that's what I modeled. And then I threw in some uniform pressure, 2.5 on this side, 1.5 on this side, just so that I can throw some torsion onto this wing box. Otherwise, it'd just be straight bending. There wouldn't be any torsion that would come out of this. And as for constraints, this can be a symmetric bending case. Usually, you analyze the symmetric. So it's left and right hand side of wings see the same load. So I can use structural symmetry there and only model half of the wing, and then apply the right constraints at the boundary. We've already gone over that with some of our homeworks already. So, and the last thing to constrain, since I've decoupled the wing from the fuselage, I need to model in the constraints for how the wing attaches to the fuselage. So, I guess I'll go over the FEM right now, and these are just some pictures of the actual deflections that I'll go over right now. So I use primarily FEMAP at work, which goes with Nastran, but I have used Abacus, and I have used Patran, which not many people use. Patran is really one of the first ones because it was Patran and Nastran. But now we have, I think, a lot better software, a lot better. Anyways, so I'll just quickly go over in FEMAP the actual model. So you can see you start off with your geometry. So the designer will give you some kind of geometry. It's straight imported from the CAD. And I just created that quickly. You can see the 7 ribs and so on. And so
Christian, can you tell me when they give you the model, it's probably a solid model?
usually designers will give you a solid model. So you have to, if you're really good buddies with them, you can ask them, hey, can you give me mid-plane surfaces of, say, for example, the skin? Otherwise, you have to do it yourself. So you have to know you have to be able to work your way around CAD, either in the CAD software and export the clean surfaces that you want, that you saw here, or you have to mess with it in FEMAP, Abacus, or whatever other software. You're generally never going to create your own geometry within the preprocessor. But it has the capability, although it's very limited. But it's advised to just do it outside and bring in the clean geometry, because cleaning up the geometry can take a while depending on how good your designer or bad he is. So here this was easy. I just created the lines, extruded it, threw some surfaces together, put it together. And so I start off with that, and then I go off to my actual element types. So if I go here, let me show you.
Everything here is split in, right?
Everything here is plate elements and beam elements. I could have used rod elements. I'll show you why. One of the slides that I saw in Vinay's PowerPoint was some of the typical issues. And we have beam elements, right? I can represent this whole I-beam that you see here as one beam element, but I can't do that with a wing box. How am I going to connect the skin to it? How am I going to connect the ribs to it? I can't do that in this application, although it has its applications. So what I do is I have to take my I-beam section. I'll model the web as plate elements. So this is all plate here. And then my caps, I'll model them as rod elements. Or I'll model them as beam elements if I really care about anything other than axial load going through those spar caps. Here, I threw in beam elements just because. Other than that, everything else is 2D plate elements. And so that's what you see here. I have some bar elements, which are the beam elements. They call them bar. And the plate, you can see they're linear elements, and there's a lot of them. And they're all connected here. Out here, you can see 3, 4, 5. This is the symmetry constraint. 3 goes with the x direction. 4 and 5 goes with the 4 is the rotation about the x, and 5 is the rotation about the y. So in this plane of symmetry, that's where you would constrain the out-of-plane direction, and you would constrain the out-of-plane moments. And then here's my wing to fuselage constraints. So here I constrained it, I pinned it 1, 2, 3, so it's not allowed to move. It can rotate. That's why over here I simply applied a vertical constraint. So that way it's fully constrained. So this would be some kind of pin joint that would be on my spar, and it would connect mate to the fuselage there. And over here it'd be some kind of a lug or yes.
Are any of these composites?
No.
But in your application, they're probably composite.
Yeah, I deal with mainly all composite, but it's just really the loads portion doesn't change in terms of extracting the loads. The loads that you see in the composite, it's going to be the same procedure. It's just how you size it and how you what kind of theory you use. So there's laminate theory, and the buckling is pretty similar, because buckling you can get your laminate properties, which are your isotropic properties for the composite from your ABD matrices. I won't go too much into that, but so you can see I have all the ribs there. I'll go on to the next thing. Material, I just threw in aluminum. So you can see it's 10.3 to e to the 6, Poisson's ratio of 0.3. Properties, similar procedure. You always create you always bring in your geometry, you throw on a mesh, you create your material, you create your property, you assign the property to the element, and therefore it's fully defined. Here I have a bar property for all my bar elements, and then one simple plate property for all my plate elements. And here's where you throw in the thicknesses, and here's where you throw in the dimensions of your cap, 2 inches by 0.1. You assign the orientation for those bar elements, because it can be oriented this way, so you assign all that in there. I won't go into that. And then the loading, simple pressure loading. Oh, here I have 1 by 0.5. You can see it. There's 1 here, 0.5 here. I think in the slides it had 2.5 by 1.5, but
I don't follow. What is that?
this is the pressure loading on top.
yeah.
Okay.
So you do that different to have closure?
Sorry?
So you do different so you have
Yes,
closure?
I made it different so that I can do some kind of torsion. And it follows generally where the center of pressure is for a wing. It's like about quarter of the way, 25% in front of the leading edge. Typically, it moves to the center if you're going above Mach 1, but I'm not going to go into that. This is just, for what we do, we don't generate our loads. There's a different loads group, so they generate loads for us. So we build our finite element model. The loads group creates loads based on not necessarily CFD, but they have other software, simpler theory to come up with loads. And they produce those loads based on what mass properties feeds them. Mass properties has to track all the weights, and so you need your weights, you need your inertias of your aircraft to be able to predict the loads, and that's the cycle that they go through, and then they produce loads and give it to us after we give them our FEM so they can apply the loads. And then we run our analysis. So the applying loads portion you don't really do, at least in a big company where every group is has their own job function. You might do it at a smaller company, but I talked about the constraints. So once you throw on a mesh and do all that, you're ready to run it. You're ready to set up your job, which is what I did here. I have one for Abacus and one for Nastran.
Can you discuss the beams more?
The beam, how they're used.
Yeah.
So, as I was talking, the beams are used to represent the caps of the spars only. So the I-beam has the web, which is the vertical, and the caps. And so in the beams, I have my shape here. So here's my Z direction. Here's 2 inches, 0 to 2, and 0.1. And that's where you input it. And that's what you see here. They're rendered. I rendered the beams in here, so you can actually see the beams. So it's more to help you visually and it'll help you with orienting this Z direction of these elements.
So that beam is taking the bending moment?
It takes a little bit of the bending moment. The way you figure that out is you look at the running loads in the skin and you compare that to the axial loads in this beam element. And typically, you can make this take the bending loads if you make it thick enough and you make the skin thin enough. It all comes down to stiffnesses of the wing of the cross section. Is the spar cap going to be stiffer than the skin? So it's up to you. So you can play around with that. But typically, since the skin is closer to the OML, it's farther away from the center. So if my wing is like this, if my wing is like this and it's taking bending this way, the bending stiffness is a function of distance with respect to that axis, right? So if my skin is above my spar caps, it tends to have an advantage in terms of that it's further away from there. You can give it more bending stiffness, more inertia versus the caps. And I have a longer running area for my skin. So typically what we do, since I work composites, what generally in practice we use for a composite skin, we like to have the skin take the bending loads, because I can tailor my plies so I can give it the stiffness that I want in bending, and I can't really tailor my plies for a substructure which is usually metallic. You do see some composite substructure, but you can't. You're not able to tailor it like you can the skin. So based on your bending moment and your torsion, that'll dictate usually what percentage of 0s and 45s your skin is going to have. Because torsion, your 45s and minus 45s take that load, whereas your bending is your 0s. So usually you have a low percentage of 90s in there, because 90s would be the fibers running this way, but no load is really running in that direction. It's shear, which produces tension this way, compression this way, either way you look at it. Those are the 45-degree fibers, and your 0s running this way are taking the bending loads. So it has its advantages with that. That's why you typically see composite skins and metallic substructure. So once you're done with that, you can FEA lets you choose whatever solver you want. You can export the input file in Nastran, Abacus. So each of them has their own structure. So you can see here this was output from FEA, and you can see you're already familiar with this layout. You start off with your nodes. It says Abacus here. Nodes. I think I have like 1,000. I'll just go nodes, and then you go to elements. Here it starts listing element. These are the beam elements. So it's a 3D beam element, linear, 3-1. And then you go off to, here are my S4, which we just went over. There's the quad elements. The S4 is right there. It could be S4R if you want to make it reduced integration. Then you have more beam elements. So it output them based on the groups that I have for spars and caps. So I don't have to go into that. So next one, there's more quad elements, S4. There's a good amount. So here are more beam elements, S4. See, did I miss more beam elements right there? More quad elements. More beam. Okay. You can see it commented out. FEA comments out the group. FEA calls them groups. Abacus calls them sets. So it's just a way of organizing your model and say, I have these elements. I want to keep track of these elements. They're a specific group. And so I call them upper skin. And here you have your lower skin group, my spars, my ribs. You generally don't do this, but with big models, it helps you keep track of different portions of your model. And so, let's see, more comments. Here's the bar property. In Abacus, it's called a beam section. So property, FEA, section, Abacus, kind of a comparison between the two. More materials being defined here. Here's my section for my beam. You can see the points, the corners, -0.1, and 0.2. You can see that those are the cap section, because I made it 2 inches by 0.1. And here's the centroid, and the shear center for that particular beam element. So here's the aluminum property, and here's the step. For some reason, FEA just says, I'm going to assume that this Abacus input file you want is going to be, it defines a step 0 and a step 1, but it's still a static analysis. So ignore this frequency. You can take these out and it'll still run. This is just the way FEA outputs the input file. And then here you can see the constraints, the 3 direction, the 4, the degrees of freedom. So remember the 3, 4, 5, that is the symmetry constraint at these nodes. And then we should see some 2s and 3s. Here's a 2. That has to be the front spar because I constrained that in the vertical. Or it could be the aft spar because I constrained both of them. And here's the loads applied. So it looks like it resolves that pressure into, I want to say this is a node, but I'm not sure. It could be a node or it can be an element pressure, because you can also apply pressure on it.
It resolved in the nodes.
It's the nodes? Okay.
Can we,
Okay.
yeah.
Yeah. So I think we've gone over that. And kind of just want to go over the results now at these slides. So once you run it, I ran it in Abacus. I created the model in FEMAP, but here are the, you can see the deflection. I threw in arbitrary numbers, so I don't know what to expect. I could run hand calc analysis and determine what it should be. I could throw in, determine my wing bending inertia, my EI value basically, by hand. I know my E. I can find my I based on parallel axis theorem and assuming everything is a square and doing all that. Just build a spreadsheet with that. So here we were talking about line loads, right? So my NX values, so these are my compression loads and my tension loads. And you can see it being plotted on the elements themselves. Here, Abacus calls them section forces. In this particular case, it's SF1. So you have to really read the documentation and know what you're reading, because you can transform these into any direction you want. More circle kind of stuff. So you can.
But these are the NXX discussed.
Yeah, exactly. So this would be, if my element x direction is running this way, this would be my NXX. That's what I'm plotting here. You can see, since it's a lot deeper in the middle, you're going to see this is taking more line load than sections out here. But because I made it equal thickness, this is exactly the opposite value of that, just the positive and negative, if you were to kind of zoom in on that. And here's just the shear loads. Usually what sizes the skin is mainly your compression and tension loads.
Is it NXY now?
Yes, so this would be S12, or yes. This is SF3 actually.
That's
So-
NXY.
Yeah, but Abacus calls it SF3 right here. So it's shear membrane force in the local 1-2 plane. So we were talking about 8 different outputs for the quad element that Vinay was just talking about. Here's how it outputs in FEMAP. And you can read the description and be able to understand, okay, that's my NXX, that's my NXY, and so on. So this is my NXY. Here's my substructure, my shear NXY, or SFS12, that concept. And I just kind of noted here's where I constrained the wing to the fuselage. And if you can visualize, I'm bending this. These are able to take vertical load. So as shear comes across these spars, it kind of gets dumped into these constraints here, or would get dumped into the fuselage in the real world application. Those loads would travel to the fuselage. So here, this portion, you can see there's no load here, because the load basically shears into the fuselage, here and here. I think I might have constrained it here, I'm not sure. But here, there should be very little shear, hardly anything, because we constrained it here. So imagine this is where my fuselage is coming in. So this portion of the wing is what you see, and this is what they call is carrying through the fuselage. So very, yeah.
Shear is that Z direction, or what shear is that?
This is shear due to bending and torsion. So, yeah. So torsion, the shear comes out through these as a couple. So the shear is produced by torsion, and you have to react that with a kind of a force couple in the opposite direction. So if you were to read the SPC forces at these nodes where I constrained it, you would see them going in the opposite direction. They better match the torsion you applied. So those are some of the checks that you usually do. You look at your loads and you tell yourself, do these make sense? So for the wing bending, you look at these line loads. You know the length of the elements. You know the line load, which is force per unit length. You know your total load of that skin, and you know your distance between the two. You should be able to back out the moment that was applied, and you should be able to confirm the bending moment that you applied to this entire wing. matches that. And the last thing is check your spark cap loads. So you were saying, how do you know how do you know if the spark caps take the bending versus the skin? So this is one way I would confirm whether the spark caps took it or the skin took it by comparing the total load here. The spark cap loads that you see here are not force per unit length. These are actual forces. So you would compare this force, which I can't really read from there, like 500 pounds. You'd compare that to your line load in your skin by converting that to a force because you know your element lengths, right? And so that's how you can tell. You ratio it. Usually the spark caps will take like 10% or 5%, and the skin will take the rest if I'm going for a stressed skin design. If I beef that up and I thin down the skin, you'll see a lot more axial load in those spar caps. And I think that's what I have for now. You guys have any questions? Yeah. We're good? All right.